Hello, everybody. Let's go over your homework a little bit and see if we can answer some questions for you. I'll be jumping back and forth with some Word documents. Hopefully, you guys can see this all right. Let's go through this kind of quick because some of it could be lengthy and a little bit long. So, um, we're talking about binomial distribution, questions that involve, does it have a success? Does it have a failure? Is it independent? Number of trials is obvious. And the probabilities are basically the same on each of the trials. So let's go through these kind of real quick. Hopefully my calculator pulls up. We can look at some stuff on that. Last time it didn't show really well. So again, kind of getting used to it, but I want to help you out on your homework. All right. Each of the following situations. Number one, determine whether or not the given random variable is a binomial distribution. So we go to a bookstore. We got top read shelf. 4 out of the 20 books are by the same author. Suppose you select 3 books from the shelf at random. X is the number of books that are by this author. Is this a binomial type of situation, a distribution that we would use? Since we're selecting 3 books, that is the number of trials. Um, let's see, 4 out of the 20 books are the same author. When you select one book, when you select the other one, that one book has gone away. So the probability kind of changes a little bit. Remember, in a binomial, it's got to stay the same. So number 1A should be no. Um, it's not a binomial situation, binomial distribution. Okay. Internet at a certain cafe. It's not working 4% of the time. You and 4 of your friends, how many? 5. Each go to the cafe once at a random time over the span of a month, independently of one another. Why is the number of people in your friend group who go to the cafe? They can access the internet. Remember that we use the word acrostic bins to help us out, deciding if something has a distribution that's binomial, as opposed to the other ones that we've been studying, uniform distribution, normal distribution. Is this a binomial distribution? So let's see. Is it binary? Well, yeah, it's got a chance of success if a person goes in 96% of the time, this thing works. 4% of the time, it does not. So it's got a pass or a fail kind of a situation. Is it independent? Well, yeah, it tells us it's independent one of another. Let's see. Is there a certain amount of trials? Um, it looks like you can pick that month there, but really it's you and your friends, I think. You and your friends going in. So there are 5 people, what's the probability? Um, one of them, right? They didn't really give us a problem to do. We're just saying if the situation's binomial or not, right? And is it constant over that time period? And it looks to me like it would be. So yeah, part B is follows the situation or the suit of a binomial distribution. All right. So let's get into some of these problems really, really quick. In the game of Mac, you roll 6 dice. So we got 6 trials, it looks like, 1 dice at a time. You earn 100 points for any one die that lands on a 1, 50 for a die that lands on a 5. No points are earned for any other number. X is the number of dice that earn points from the initial roll. Why is X a binomial? Well, you got pass or you got fail, right? You've got independent trials. Yeah. When we roll dice, there's not one dice that really rely on the probability of another dice rolling a certain number or whatever. Okay. Are the trials, number of trials fixed? Yeah, I'm rolling six, right? Six. And the next question it says, 4 out of 6, right? So six is our, number of trials that we have. And let's see, on each trial, is the probability the same? Yeah, the probability number would be the same. So the probability of success would be this. Well, what's the probability um, that a die lands on one, right? Well, that's 1 out of 6. And we also win if it rolls a 5, right? Well, that's also 1 out of 6. The probability of total success, well, these are added together. And so we would say 1/6 and 1/6 is 2/6, reduce 2/6, and that's 1/3, right? So that's the probability of success. The number of trials is 6. There are 6 dice that we do. Okay. What's the probability? 4 out of the 6. All right, we're going to go to our calculator now. All right, go to our calculator and we're going to look up. It's a binomial process. So let me go to my scratch board over here. Let's see, scratch board over here. So the probability, hopefully you can see this, that x equals 4. That's what that looks like. All right, we've written that before, okay? Well, that's going to be equal to, all right, that's going to be equal to, well, I've got 6 total chances, and I'm going to choose 4 for this scenario to be successful, right? So we go into our formula like we've done before, right? And it's really not a formula, we just been piecing it together, and it's given to you on your AP exam. Well, what is the percentage that I succeed? Well, I win. What did I say? If a 1 rolls, that's a 1 out of 6. I'm just going to write it down here. Okay. Plus, if a 5 rolls, that's also a 1 out of 6 probability, which gives me 2/6, which is really 1/3. So 1/3, right? And I want that to happen 4 times. So I'm going to raise it to the 4th power and multiply it by its failures. And how many times do I see that? Well, out of 6 times, it'll be 2. It'll be 2 right there, right? Ugh. All right, so let's look at this a little bit. Let's see, 2 out of 6. Well, it would seem to me like the failure would be the numbers 2 fails, right? The number 3 fails, the number 4 fails, and the number 6 fails, right? 1 out of 6, 1 out of 6, 1 out of 6, 1 out of 6, which is, well, 1/3, and they all have to add up to 100%. Well, that would be 2/3, right? All right, well, let's put all that in my calculator, and you probably won't be able to see it, and I'm going to check my answer, make sure we're right. So I'll go 6, and I'm going to choose. Remember, we go to math, probability, choose 4, right? Well, there's 15 ways that can happen, okay? And I'm going to do parentheses because I'm going to put, 1/3 in a decimal, or not in a decimal, but a fraction. 1/3, and I'm going to raise that to the 4th power, right? Right? We're going to multiply that by 15, right? And then multiply that by 2/3 raised to the 2nd power, right? And I get like an 8%, 0.0823. Let's see what our answer is here. 0.0823. Yeah. And we are good right there. And that's exactly what I put in my calculator. I did the 1/3, 2/3. Hopefully you can see that as well. There's an 8% chance that I would succeed in playing that game right there. Okay. All right. Very good. Very good. Again, let's see. Let's see. Probability it rains in London in April is 30%, right? So the probability it doesn't rain is 70. So already we got a binary kind of a statement. Kier will lead walking tours 5 randomly selected days. She says that the probability of it raining on exactly one of them out of the 5 has the same chance of it raining on exactly 4 out of the 5 days. Since there are 5 ways to choose one and also 5 ways to choose 4. Well, you know what? I think I know what she's saying here. If I put in my calculator, oh, they put it down here. 5 choose 1 is 5. And, you know, 5 choose 4 is also 5. That's true. You know, there are 5 ways to get a certain scenario. There are 5 ways to get this other scenario. That's fine. However, when you're actually doing binomial probability, those are kind of set up in a little bit different manner, right? For example, let's say this. Let me clear all this out of the way. Clear all this out of the way, please. And let me help you out. 5 choose 1 and 5 choose 4. Same kind of thinking. Same kind of thinking. Let's set both of them up in a probability kind of a manner, and you'll see how it's a little bit different. The probability, what did they say? Does it say at least one day? Did it say at least one day? Exactly one day and exactly 4. Okay, that's a little bit different. All right, so the probability that X is 1, right, is the probability that I have 5 days. I'm going to choose 1, right? But we're saying the chance of success is 0.3. I think she said 30, right? Out of one of those days, raised to the 1, right? But it's going to fail 0.7 4 of those days. Okay. That's a lot different than saying the probability X equal 4. Well, you're still going to get 5, choose 4 here. 5. That's going to be the same. How many ways can 4 successes happen out of 5? You know, that's going to equal 5. That's the same thing. However, your probability is a little bit different, right? So 0.3, but this time I want to raise it to the 4, and it's going to only fail 1 time. That's a lot different probability error. So her reasoning, this part, that part, that's the same. But the total probability, you need a little bit more information out of that. You know, that's a binary statement. So I can set up this equation like normal. But for her just to say only this part, you know, that's kind of false there. You know, so we don't really agree with Kira's reasoning on that one. Okay. All right. Very good. Very good. Company sends out weekly newsletter to people who are on their email list. Weekly email, 38% open rate, meaning 38% of the people click on the email in their inbox to read it. Suppose we take a random sample of 10 from a very large email list that's selected. Consider the probability that exactly 6, X equals 6. My gosh. X equals 6. Define the random variable of interest and state how the random variable is distributed. Is it normal? Is it uniform? Is it binary or binomial? Right. Well, we've got a success and fail. Right. We've got is it independent? I'm going to assume that it's independent. one person opening mail is not going to be dependent upon anybody else opening mail. It's just, it happens. They're in front of their computer. Is the number of trials fixed? Well, yes, six out of the 10. So we have, 10 people. And does the probability sustain? Does it remain the same? Yeah, 38%, right? Uh, Throughout all of them. So the probability that a person is selected to, click on the email in their inbox to read it. That's what we're saying. And this is a binomial distribution. That's how we'll read it. All right, calculate the probability that exactly six. So I'm going to throw it straight into my calculator. We'll check our answer. Okay. Again, hopefully you can see my calculator. If not, just listen to me. And we did this in class. So TI-83 is a little bit different than the TI-84 when it comes to combinations and permutations. So in my 83, I've got to hit six, math, go to my probability, choose, right? Oh, I did that backwards, didn't I? Yep. Let me clear out of that. 10. I got 10 trials, 10 people, and I'm going to choose six, right? We're going to multiply. There's 210 ways that can actually happen. We're going to multiply that by our success, right, which is 0.38, right? And we're going to raise that to, I want six, and we're going to multiply that by the fail rate. Well, if 38% succeeds, what is that? 62% would fail how many times? Well, if I want six out of 10, fail four times out of the 10, right? There we go. Oh, I did 62. Doggone it. 0.63, I'll say 23 times 0.62 raised to the fourth power. I got a 93% chance that happens. That seems kind of high. Seems kind of high. Oh, I guess so. And there we go. No, not 93%, 9% chance. Sorry, read it wrong. Read it wrong. There we go. Right there. All right. As long as it's binomial, we're good. Yep. And make sure, again, we include the number of trials, right, and the probability of success. All right. Hopefully you're understanding this and can get it kind of quick. What kind of distribution, do we have here? So we talked about normal before, uniform before, even with discrete variables and bar charts. This is a little bit different. All right. Tough one here. Number five, real quick. And I think the last two are multiple choice. So let's get to these real quick. Joseph Girard, this is not made up. He is actually a Clemson basketball player, holds record highest free throw percentage men's college basketball, reported by the association governing college athletics, the NCAA. His free throw percentage, 95%, represents the percent of free throws he successfully makes. Assume that he maintains this success rate. That's a part of a binomial probability right there. Assuming he maintains this. And that is free throws are independent. That's all set up for binomial. Consider his next 94. Let X be the number of free throws he makes in the 94 free throw attempts. How many of the 94 do we expect to make? Well, he's already made 95% of all of his shots. So we're going to say 95% of the 94, I expect him to make 89.3, or if we want to be really discreet, 89. Okay, something like that. All right. So let's calculate what's the probability, that the number of free throws that he makes out of 94 equals 89. Well, I'm going straight to my calculator. All right, straight to my calculator. And we're going to say out of 94, so I'm going to click 94. I'm going to choose. Well, what do I want? I want 89. How many ways does that happen? My gosh. What is that? No, that's 54,891,000 ways that can happen. That's a lot. Thank goodness for calculators, right? Um, multiply that by the probability of success. Well, I've got a 95% chance of making them, and I'm raising that to what do I want? I want 89, right? I want 89 out of 94. 89 will be my success rate. Enter, very large number. All right, I'm going to multiply that by my failures. Well, if 95.95 is success, 0.05 is my failure. I'm going to raise that to, well, I've got 89 already accounted for, so I need 5 more to make the 94. I want to know 89 out of 94 is going to be made. Okay, multiply all that together. The probability that happens 17.9. Hopefully that's right. Hopefully that's right. I'm gonna check that one real quick. The probability of 89 out of 94. Ooh, what I say? 1 7. Ooh, I got it right. It just looks odd. Looks weird. 17%. I mean, he's a 95% free throw shooter, but that's a lot of attempts. That's a lot of attempts. What's the probability? Him getting 89 out of 94. That's deep right there. Wow. All right. So last thing, calculate the probability he makes at least. All right. Let's go into this one, and I'm gonna let you guys calculate this one. This is not equal to. Okay. So this is going to look like something like this. I'll show you. I got to go back to the question. I forgot it. The probability. Did it say at least? I think it said at least 92. All right. This is how you do this one. The probability that he makes his free throw, random variable X, is greater than or equal to 92. In a binomial distribution, the way that we do that is just simply this. The probability, I'm going to let you guys do it. Probability X equals 92 plus the probability X equals 93, right? So on and so forth until you get, what is it? X equals 94. Is it 94? Yeah. So we're going to add all of those up together, and probability 92, probability 93, and the probability of X equaling 94, all of that equaled up. That's going to give us the probability of him getting greater than or equal to 92 shots. All right, I'm going to let you guys do that one on your own. A little bit of calculations in there. I just showed you a little bit how to do it. Very good. Each of 12 classroom teachers has an elementary school, 2 from each grade level, kindergarten through 5th, young people, 2, still young people, but a little bit older. They're randomly selected. 1 student from their class. Each of the 12 classroom teachers. You got 2 from each grade level. Randomly select 1 student. Okay, we're going to select 1 kid. All right, I got mixed up. There's 2 teachers in each grade level, looks like. Ask them about their bedtime. Let X be the number of students who have their bedtime later than 8 p.m. Which are the following best reasons why X is not binomial? Let's see here. there are more than two possible outcomes since the number of possible bedtimes is infinite. I don't think so. More than two possible outcomes. No, we're talking about still kind of a range here. That's not really necessary. The teachers don't choose students independently of one another. Maybe, but let's go on to the next one. The number of students being chosen is not fixed. Now they said one up here. A one in different classrooms. Probability of choosing a student with a bedtime later than 8 p.m. likely differs by grade level. So I think that one's the best answer. Remember, the success probability, success, failure, whatever the percentage might be, it has to remain the same over the entire, you know, calculation of your problem. If I flip a coin, and I do that through binomial probability, um, the chance that it lands on a head can't change while I'm still trying to calculate the mathematics of it, right? Because and it just won't come out right. So I think D is the best so far. Let me see what E says. 12 teachers weren't randomly chosen. We'll get into that kind of a little bit later about our samples and choosing things like that. But no, this one right here. Yeah, if you're younger, your probability of going to bed closer to 8, increases. As you get older, you're going to go, to bed a little bit different. So, this study is not the greatest. So I would say D is better, right? Pretty good question there. People drive Department of Motor Vehicles. Oh, this one's not. We got to calculate this one out. Their eye color is recorded. Proportion of people who's got blue eyes, 27. Probability that at least, here we go. Bam. At least, not equal to, right? But at least. So remember what I've said before. And I might let you guys figure this one out as well. Hopefully you can see my scratch pad here. Remember what I've said before. I've said that the probability of at least one, isn't that the same as one minus the probability of none? That's the same thing. I mean, you could say the probability of one plus the probability of two plus the probability of three. You could say it like that. This is a little bit easier, I think. All right, so let's try to do some calculations with that. Let's make sure it's a binomial. I mean, they got calculations here for us, so I'm assuming that it is a binomial, but we can go back through it. Is it binary? Is it success, failure? Well, yeah, somebody with blue eyes, 27%. So that would mean somebody who's not is 73%. Is it independent? Independent. Assume that this is independent. Okay. Let's see. Is the number fixed? Well, yeah, I got 5 people that we're trying to look for. Okay. And does everything remain the same? Well, yeah, that probability won't change as we go through the 5 people. So I'm going to say this. I'm going to say one minus the probability that none, right, are blue eyes. So here we go. Let's do it. So let's say And you can do it out all the way if you want to. Um, let's say, and we're looking for none, right? The probability, so I'll just do it all the way. 5, choose, and just see what it looks like. 5, choose 0, you know. Well, what the heck's that going to be? Well, it's going to be 1, right? There's only one way that can happen, out of 5 times. So it's always going to be 1. So we're going to multiply that with uh, the successes that I have. Well, really, uh, if I'm looking for nobody, uh, wouldn't that be point? What I say? What is that? 0.73 raised to the fifth. I want them all to fail. What would that be? That's like a 20%. All right, so all of that is like a 20%, that it's not going to happen. But remember what we're doing. We're doing 1 minus all of that. Okay. 1 minus all that. And the way I do it in my calculator, I just hit the answer right here. So I don't have to type it all in. Second answer. I got 79.26. That's the exact same thing. So it should be this right here. That's the exact same thing as saying the probability of at least one is the same thing as 1 minus the probability of none of them, right? So that means all 5 of the people are not blue-eyed, right? There it is. Hopefully I explained that okay. Uh, and I think that is it. No more problems there. All right. Binomial distribution. Hopefully you enjoyed it. Hopefully you like it. Hopefully you get the sense of what you're looking for in some of these word problems. If it fits the acrostic that we use, hey, we're going to use this type of kind of formula, but it's really a reasoning. How many different ways can it happen? And we're going to multiply it with the successes and multiply it with the failures. All right. And we'll build on that a little bit more as we move into geometric. All right. Hopefully that helped you guys. Hopefully you enjoyed that. And we will see you guys a little bit next time.